Imagine thousands of powerful AI chips, all working together on the same problem. One chip processes part of the information, another chip processes something else, then they need to exchange their results, again and again, at incredible speed. But here's the problem: modern AI systems are becoming so powerful that the biggest challenge is no longer just making individual chips faster, it's moving enormous amounts of data between them. An AI model may need thousands of processors working together. And if those processors have to constantly wait for data, all that computing power becomes less useful. So how do AI chips communicate so fast? And why are engineers now trying to use something much faster than ordinary electrical connections, light? To understand the problem, let's start inside a modern AI data center. Imagine a huge building filled with rows of computing racks. Inside those racks are powerful processors designed specifically for artificial intelligence. These processors perform enormous numbers of mathematical calculations. They process images, language, video, scientific simulations, and increasingly complex AI models. But a single processor isn't always enough. Large AI workloads can be divided between many processors. That means the chips constantly need to exchange information. And this communication has to happen extremely quickly. Imagine trying to run a conversation between thousands of people. But every person has to wait for a message before continuing. The entire system would slow down. AI computers face a similar problem. The processors may be incredibly fast, but if data cannot move between them quickly enough, the whole system becomes limited by communication. This is called the interconnect problem. Traditional systems use electrical signals to move data. Those signals travel through extremely small metal connections. For short distances, this works very well. But as the number of chips increases, the amount of data increases too, and electrical connections have physical limitations. They consume energy, they generate heat, signals can weaken over distance, and moving huge amounts of data through increasingly dense systems becomes more difficult. This creates a strange situation. Engineers can build faster processors, but connecting those processors together becomes one of the hardest parts. So what is the alternative? Light. Instead of sending information using only electrical signals, engineers can convert data into optical signals. Tiny pulses or changes in light can represent information. That light can then travel through extremely small optical pathways. This technology is known as silicon photonics. The idea sounds futuristic, but the basic principle is surprisingly simple. Use photons, particles of light, to move information. Imagine a tiny highway built directly into a silicon-based system. Instead of electrons moving through a metal wire, light travels through an optical waveguide. The waveguide guides the light where it needs to go. And because light can carry enormous amounts of information, it becomes extremely attractive for high-speed AI systems. But how do you put light inside something as small as a computer chip? That's where the engineering becomes fascinating. A silicon photonic system can contain tiny optical components. There can be structures that generate or receive light, components that modify the light, and microscopic waveguides that guide it. The electronic system creates information. That information can be converted into an optical signal. The light travels through the optical pathway, and at the destination, the optical signal is converted back into an electrical signal. The process happens incredibly quickly, and it can happen billions of times, but engineers are trying to take the concept even further. Instead of keeping optical components far away from the processor, they can be integrated much closer to the computing chip. This is where co-packaged optics becomes important. The idea is to place optical communication technology very close to the main processor. The shorter the electrical path, the less difficult it can become to move enormous amounts of data. And this matters because AI processors are becoming extremely powerful. Modern AI workloads can require enormous bandwidth between processors and memory, and when thousands of processors work together, the communication network becomes just as important as the processors themselves. Think about a massive AI cluster. Instead of one computer, You have hundreds or thousands of computing units. They need to exchange information constantly. If the connection between them is slow, the processors may spend valuable time waiting. But if communication becomes extremely fast, the entire system can behave more like one giant computing machine. This is one reason optical interconnect technology is receiving so much attention. Recent industry and government efforts are specifically targeting silicon photonics for AI infrastructure, including research into higher speed and more energy-efficient optical links. But there is another major advantage: energy. Moving data is not free. Every electrical connection consumes some amount of power, and when you're operating a huge AI data center, small energy costs can become enormous when multiplied across thousands of connections. More power also means more heat, and heat is one of the biggest problems in modern computing. AI processors already generate enormous amounts of heat. Data centers need sophisticated cooling systems just to keep them operating safely. So if engineers can reduce the energy required to move data, they may also reduce some of the heat associated with communication. This doesn't mean optical systems are magically free of energy consumption. They still require lasers, electronics, conversion systems, and other components. But their potential efficiency at very high bandwidths is one of the reasons engineers are investing heavily in the technology. There is another fascinating part of optical communication. A single optical connection doesn't necessarily have to carry just one stream of information. Different wavelengths of light can be used to carry separate data channels. Think of it like multiple invisible lanes traveling through the same optical pathway. One wavelength carries one stream, another wavelength carries another, and another carries something else. Together, they can dramatically increase the amount of information traveling through the system. This technique is known as wavelength-division multiplexing, and it is already widely used in optical communications. Now imagine applying similar principles to massive AI computing systems. Instead of relying entirely on traditional electrical connections, future systems can combine electrical computing with optical communication. The processor performs the calculations, optical systems move the data. Electronic and photonic technologies work together, but there are still major engineering challenges. Light doesn't automatically solve everything. Engineers need extremely precise optical components. They need reliable lasers. They need efficient conversion between electrical and optical signals. They need accurate alignment. They need advanced packaging. And they need manufacturing processes capable of producing these components at enormous scale. This is especially difficult because AI data centers require huge numbers of components. A technology may work perfectly inside a laboratory. Turning it into millions of reliable products is a completely different challenge. Manufacturing becomes critical, packaging becomes critical, thermal management becomes critical, and even the physical arrangement of the components matters. Engineers are therefore working on ways to integrate photonics more closely with electronic processes. The ultimate goal is simple: move more data, faster, with less energy, and with lower delay. This could become increasingly important as AI models grow. Today's AI systems already require enormous computing resources. Future systems may need even more processors working together. The amount of information moving between those processors could become staggering. At some point, making the processors faster isn't enough. The communication network must improve too. And that is why the future of AI may depend not only on better chips, but on better connections between those chips. This is a subtle engineering problem. Most people think AI progress is mainly about bigger processors, but behind the scenes, there is another race happening, a race to move information, faster connections, higher bandwidth, lower power consumption, lower latency, better packaging, and increasingly, more use of light. The most interesting part is that this technology doesn't necessarily replace electronics. Instead, the future may combine both. Electrons can handle computation. Photons can handle high-speed communication. And advanced packaging can bring the two together in extremely compact systems. If engineers can make this technology reliable, efficient, and affordable at large scale, AI data centers could connect enormous numbers of processors much more efficiently, and that could change the architecture of future computing systems. So the next time you hear about a powerful new AI chip, remember, the chip itself is only part of the story. The real challenge is getting all those chips to work together. They need to share information, they need to synchronize, they need to exchange massive amounts of data, and they need to do it without consuming impossible amounts of power. That is why engineers are looking beyond traditional electrical connections and towards something that has been moving information for billions of years. Light, tiny photons traveling through microscopic engineered pathways, could become one of the most important technologies connecting the AI systems of the future. The processors may do the thinking, but the connections determine how quickly the entire system can work together. And in the race to build larger and more powerful AI machines, the fastest computer may not simply be the one with the best chip. It could be the one that moves information the fastest. If you enjoyed this engineering documentary, subscribe for more fascinating stories about AI hardware, semiconductors, automation, machines, and the engineering technologies shaping the future. I'll see you in the next documentary.